Hi, I'm Seunghoan from Nagoya University. It is a joint work with my advisor Masahito Hayashi. The title of this talk is Capacity of Quantum Private Information Retrieval with Colluding Servers. Private information retrieval is a retrieval protocol without revealing which message is requested. I'll call it PIR in short. PIR can be understood easily by comparing with the usual retrieval scenario. Let's say that a server contains F files M1 to MF, and a user wants to retrieve the kth file MK. For this, the user sends K, the server returns MK, and then the user knows MK. However, in this case, the server also knows what is requested, so K is leaked. On the other hand, in PIR, we require this K is secret to the server. So in PIR, the user sends a query Q instead of K and receives an answer A and recovers MK. Here, the user secrecy is required, which means the K should be independent of the query Q. So the server doesn't know which file is requested. At first glance, it seems very difficult to find a solution of this problem, but there is a trivial solution of downloading all files. In this solution, the user can pick the targeted file MK, but the server doesn't know which file is the targeted one. The efficiency of a protocol is evaluated by PIR rate, and the rate of the trivial solution is 1 over F, since F files are downloaded, but only one file is the target. Unfortunately, it is proved that this trivial solution is optimal. So people have started to study the multi-server PIR. The left figure is the two-server PIR. In multi-server PIR, each server contains the copy of all files, and it is assumed that the servers do not communicate. The user sends independent queries to the server and receives some answers. And the secrecy condition changes as each server do not know the K. So that is, each query should be independent of the K. Only a few years ago, Sun and Jafar defined and studied the PIR capacity. The capacity is defined as the optimal PIR rate, the maximum of the PIR rate, and they derived that the capacity is this value. Here, the N is the number of servers and F is the number of files. This capacity is much greater than the PIR rate 1 over F of trivial solution. And in our previous work, we studied the quantum version of this PIR capacity. In the left figure, the green ones are classical information and magenta are quantum ones. In this model, we assume that the servers share prior entanglement before the protocol starts, queries are classical, and answers are quantum. In addition, we considered another secrecy called server secrecy, in which the user obtains only the targeted file and do not obtain any other information of other files. Considering these two secrecies, we derived that the capacity, QPR capacity, is 1. In today's talk, we extend these results to the T-private QPIR. One critical weakness of the multi-server PIR is the restriction of no communication between the servers. So in T-private QPIR, we allow at most T servers communicate and collude to know what is the K. So some of the servers may communicate. So in this problem, the user's secrecy changes as any collection of T queries is independent of K, and it means that even if any T servers collude, they cannot know the K. And we also consider the server secrecy defined above. And considering these two secrecies, we derive the QPR capacity is this value. And it means that the remarkable result of the capacity 1 still applies if less than half of servers collude, and it decreases as more servers collude. This slide compares the classical and quantum PIR capacities. Here, the symmetric means that we also consider the server secrecy. Our result is this red one, and it is T private QPR capacity and T private symmetric QPR capacity. The classical counterparts are already studied, and our result is greater than these classical results. And our capacity result is proved by constructing optimal protocol that achieves this capacity and proving that this capacity is proving some tight upper bound of the QPR rate, which we call the converse bound. So let me start from the construction of the optimal protocol. So in the following, we will only construct the T private QPR for T is greater than n over 2. So, and you may wonder if I'm skipping the other case, but I'm not, because the other case is automatically constructed. So for to see that, I'll note that our n over 2 private QPR protocol achieves the capacity 1. If we know that this value equals to 1 when t is n over 2. And this protocol is also T private QPR for T less than n over 2, because smaller t means that less colluding servers. So our n over 2 private protocol also achieves the capacity of T private QPR for smaller t. So we only consider this case. So now we start the protocol construction. Our protocol is quite complicated, so we only explain the high-level description of our protocol. And our protocol is constructed upon the stabilizer formalism, which gives some algebraic structure to quantum theory. So I'll explain them briefly. I'll explain this stabilizer formalism briefly. The first, n-tensor system of q-dimensional Hilbert space is related to 2 n-dimensional vector space over finite field Fq. And then a stabilizer is defined from self-orthogonal subspace V of the finite field vector space. And when this subspace V is determined, some Hilbert space called chord space is also determined. So with this chord space, we can consider the following information processing task. Let's say that a state row is prepared on this chord space, and a unitary operation WS is applied. Here, the W operation is defined as the combination of X and Z operations. And then by applying some measurement on this state, which is often called a syndrome measurement in stabilizer error correction. By this measurement, we know the outcome. We obtain the outcome S plus V perp. This S plus V perp is an element of this quotient space and gives and this value gives some partial information of this operation S. So in error correction, we consider further steps, but we only use this process until this step. So using this process, we construct our QPR protocol. So first, the initial state of the servers is prepared on this chord space, and it is distributed to the servers. And then the user chooses the K and encodes this K as a queries and send the queries. And then the servers apply X and Z operations depending on the queries and the information of the files, and sends the quantum systems to the user. And finally, the user state is this state, which corresponds to this state in the above. And finally, applying the same measurement as above, the user obtains S plus V perp. So this is how the protocol is constructed, but you may notice that this protocol is not yet a QPR protocol. So for making this protocol as a QPIR, this protocol should satisfy these two conditions. First, the outcome of the user should be the targeted message MK for the correctness, and the user secrecy and the server secrecy. These two secrecy conditions should be satisfied. For satisfying these two conditions, and indeed, in our protocol, satisfying these two conditions is very sophisticated task. It is a little complicated, but it essentially reduces to finding very good stabilizer V, subspace V. So for finding this good stabilizer V, we use this lemma 5.2. The lemma 5.2 states that there exists a matrix D over finite field FQ such that the column vectors V satisfies self-orthogonality condition, and the row vectors W satisfies some weird linear independence condition. So in this lemma, the condition A defines a stabilizer because it is related to the self-orthogonality. And this condition B is used for guaranteeing the secrecy condition in our protocol. So yeah, so for explaining how our condition B helps the secrecy condition, I want to compare. I want to compare with classical case for giving you the intuition of our protocol. So the classical version of our lemma 5.2 is this condition B prime, that any T rows of the matrix D over a finite field is linearly independent. So any T rows are linearly independent. So this condition B prime has been used for many crypto protocols, such as a classical version of the PIR and the secret sharing. And these protocols send n minus T symbols by using n symbols. So similarly, in quantum case, we can expect that the twice of this n minus T can be transmitted, since we can use the both of the bit information and phase information. So finally, we use the similar structure of the classical case with the help of this condition B, and we achieve that we make our protocol to achieve that this QPR capacity 2 n minus T over n. So this is how our protocol is constructed, and for more detail, please read our paper. So the remaining is the converse bound, the upper bound of the capacity. So we have two capacity, but I only explained the proof idea of the second case. The second case is when more than a half of servers collude, as in the left figure. In the left figure, we note on the downloading state of the QPR protocol and consider and grouping a colluding servers as one and non-colluding servers as the other. And in our paper, we proved that from secrecy condition that the quantum state from colluding servers can be considered as entanglement between the non-colluding servers and the user. So like this right figure, we can consider the downloading step as a entanglement assisted CQ classical quantum channel coding. So this result from the known result, we know that the size of MK, the targeted message MK, is less than twice of total dimension of the non-colluding servers. And because there are n minus T colluding servers, we have 2 times n minus T here, and consequently, we obtain the desired upper bound as the last inequality. So here's the conclusion. So we constructed a QPR protocol, optimal QPR protocol with colluding servers, and we derived the capacity, and our derived capacity is greater than the classical counterparts. And there are many open problems on QPIR. One is the trade-off between the QPR capacity and the amount of allowed entanglement, because we assume that servers share any amount of entanglement, we achieve this capacity. But if we restrict our entanglement, we don't know if it decreases or not. And there are many classical PIR studies, so quantum extensions can be considered. Thank you very much.